Hi, my name is Jungkyu Park, and I'm one of the members of NYU B team. I'm going to share with you today some of the approaches we used in the DBTex challenge. In this challenge, we trained 2D efficient data architectures trying to find biopsy-proven lesions in DBT volumes. Here, you can see some model predictions indicated as green boxes, trying to find the ground truth lesions indicated as red boxes. As you can see, the models can have multiple box predictions per volume. Ideally, good models should output the highest confidence score for the true positive predictions. There are a number of difficulties presented by the DBTex challenge. I will discuss some of these difficulties and how we address them. The first difficulty presented by the DBTex challenge is that there's only a small amount of training data available. For example, ImageNet, a dataset typically used for deep learning for natural images, contains around 40 million images, whereas the dataset we were given in DBTex challenge has around 2600 volumes, whereas 200 of them have lesion labels. This could lead to overfitting of deep neural networks before they can learn robust generalizable features. We addressed this problem of small dataset partially by utilizing our own private data. We used around 1 million 2D mammograms and 400,000 DBT volumes from NYU Langone Health in training our models in addition to the competition dataset. Even after adding our own datasets, however, we still do not have that many positive images. We further addressed this problem of small data by modifying the input image during training. Specifically, we used the configuration from Chen et al. Paper, which involves affine transformation and horizontal flip. We apply the same transformation to both image and the label, such that the bounding boxes will still correctly indicate the lesions. This improves the performance compared to no augmentation or simple augmentation of shift and resize only. One of the problems of using a small dataset is that the models might end up learning features that lead to many false positives. We further address this problem by model ensembles. In particular, we ensemble several models from k-fold cross-validation, which is performed using the best configuration found by our hyperprimary search. This has two benefits. First, we can utilize all available data in training the models. For example, in 5-fold cross-validation, as illustrated in the figure, you can see that every image is used in training 4 out of 5 models. Second, we can detect robust features that are simultaneously found by multiple models. If different models which learned from different subsets of data agree on a set of predictions, it would and should be preferred over other boxes which only one of the models regard as important. The second difficulty of this challenge is the large volume size. In the original efficient paper, images from the COCO dataset are resized to somewhere between 512 and 1536 pixels in both dimensions. DBT volumes, on the other hand, are much larger than the maximum input size used in the efficient paper. At the same time, lesions from DBT volumes can be very tiny. Before any rescaling, the lesions can be already smaller than some of the objects appearing in resized natural images. As you can see, the lesion highlighted in red from the figure on the right can be smaller than the vehicle highlighted from the figure on the left. If we simply rescale the DBT volumes to the similar resolution, then the lesions could become almost invisible, and the models might not be able to find them. However, using the original resolution of DBT volume can also become problematic, since it can require more computation than what is feasible. If you look at the DBT volume, you'll notice that most of it is background. This is the case for the vast majority of the volumes. Our solution is to crop a smaller portion of the breast using a fixed input size. This optimal input size and locations are calculated from our dataset such that we can preserve the most amount of information. You can find the details from our data report. Once we crop some smaller portion of the breast, the subsequent downsampling, if any, will lose less information. In the image acquisition, DBT currently only utilizes about 15 to 30 degrees of limited angles in order to minimize the radiation exposure for the patients. This leads to the third difficulty of DBT data, the ambiguity of which slices have the lesions. In the figure A, we have an example of a phantom that has a red object in depth A and blue object in depth B. If you take the image and reconstruct into the 3D volume with multiple slices, then you can still see both objects from both planes, even though only one object exists in each plane. The same phenomenon is visible from the actual DBT volume on the right. On some slices, a lesion is in focus, which radiologists are capable of distinguishing and segmented as such. However, there are still other slices where the lesion is still kind of visible but out of focus. This could make it challenging for models to determine the true spatial extent of the lesions. Our solution for handling this ambiguity is to build a system that detects the center slices of the lesions. We hypothesize that if we build 2D models that take each slice's input, then the model will output the highest confidence score for the slices where the lesion is the most clearly visible. Based on this hypothesis, we propose this max slice selection algorithm which can capture this information. If you look at the image on the left, you'll see boxes with two different colors. The white box is the anchor, which is the same for all the slices. The green boxes are the predicted boxes of the model for the shown anchor from multiple slices. The color intensity of these green boxes represents the confidence score. You can see that the score of the boxes are lower on the boundary slices and the highest around the center slices of the lesion. Our algorithm is to detect these max boxes, gather them for all anchors, remove duplicates, and relocate them to the original slices where these boxes were found. Our proposed algorithm improves the mean sensitivity by about 0.1 compared to the baseline aggregation method of half-volume averaging. In particular, the biggest gain is observed around 1 false positive per volume level, which is highlighted in red. Here, you can see some examples where the model correctly found the ground truth lesions. The boxes with the most intense blue color match with the ground truth lesions appearing as red boxes. Here are some more examples of correct predictions. You might notice that these boxes might not have the greatest match, or that it's actually the box with the second highest confidence score that matches with the ground truth lesions. But predictions like this still count toward the evaluation metric of the competition in most cases like this. Here are some failure cases where the model was not able to find the ground truth lesion among its highest box predictions for these images. If we continue to look for more boxes than what is displayed here, then we will eventually find some lower confidence boxes that have great match with these ground truth lesions. However, the fact that we have to go through so many false positive boxes first in order to get there likely means that these model outputs are not useful to the radiologist, and the outputs for these images will likely not improve the evaluation metric of the competition. In conclusion, we were able to achieve the best test performances by overcoming the difficulties presented by the DBTex challenge. In order to address the small training data, we utilize additional data augmentation, and model ensembles. In order to address the large input size, we crop the most informative regions. In order to address the ambiguity in DBT volume, we built a system to detect the center slices of the lesions. Our team consists of a large number of collaborators. Kuba, Yen, and I worked on the model building. Dr. Rick, Dr. Hickok, Dr. Moy, and Dr. Wolfson gave us guidance from the clinical side, including designing and executing the data extraction and annotation protocols. The radiologists from the NYU Langone breast imaging section provided us with the lesion annotations. Professor Krzysztof J gave us guidance in model building and managed the collaboration among the entire team. With that, I would like to thank you for listening, and I'm looking forward to receiving your questions.